Okay. And so we can define conformal maps between metric spaces, and also we can say if that if row 1 and row 2 are two metrics on the same space Z, so then we say that two metrics row 1, row 2 on Z are conformal if the identity map from Z row 1 to Z row 2 is conformal. All right. Okay. Is this clear? So then that means that for all xi in Z, okay, this limit as eta tends to xi of row 2 of f of xi, f of eta. So f is the identity. So it's just row 2 of xi eta divided by row 1 of xi eta. This limit exists and is positive and finite, right? Yes. So this is the derivative of the identity map with respect to these two metrics. So it's natural to call this d row 2 by d row 1, the derivative of row 2 with respect to row 1. Does it make sense now? Yes?
Yes.
Okay. So example is del x equal to z. Then for all xy in x, row x and row y are conformal. And the derivative d rho y by d rho x is e to the bxyz. Is this clear now? Okay. Yes. Is this clear?
Yes, sir.
Okay. Now, what does this formula mean? You should understand this geometrically. So suppose let's say y is here and x is here. So then what is this Boseman function? It's the distance between the horospheres at x and y, right? So this is say y and this is say x. Yes, okay. So this is xi. Okay. So the Boseman function is this distance here, right? Is this clear? Yes. Okay. So so what does this formula mean? See, this formula tells you how big objects, the ratio between, if I have an object here, let's say a little man is here, right? then if I'm looking at this person on the boundary from y and from x, and if this Boseman function, this distance is t, then basically viewed from y, this person will look bigger by a factor e to the t as viewed from x, right? That makes sense, because if I go, I mean, y is closer to xi than x by a distance t. So what it means is, as I move along a geodesic in the direction of xi, objects will, their size will increase by e to the t if I move a distance t. Does this make sense? Okay.
Yes, sir.
So the size of objects increases exponentially as I move along geodesics towards xi. All right. Does this make sense? Yeah. And if I move away, then they get smaller. Okay. And if I'm on the same horosphere, then the objects have the same size. All right. For this point and this point here, they will have the same size. All right. Okay. So you can think of the horosphere as the set of points where objects at xi have the same size viewed from all points on the horosphere, right? Do you understand? Does it make sense? Yes? Yes, is this okay?
Yes, sir.
Okay, so we have what you can call any cat minus one space. We have a conformal structure on its boundary. That means a family of metrics which are all conformal to each other. So there is a canonical conformal structure on the boundary of a cat minus one space. Okay. Okay. But in fact, we have more than this. We actually have what's called a Mobius structure on the boundary. So we can look at the cross ratio. We can define a cross ratio of a quadruple of points with respect to a visual metric. So if suppose I take 4 points on the boundary, xi, xi prime, eta, eta prime, and I look at the cross ratio with respect to some rho x, okay? So this is defined to be rho x of xi eta, rho x of xi prime, eta prime, divided by rho x of xi eta prime, rho x of xi prime eta, right? So this is similar to the same formula that we have for the Euclidean cross ratio. So instead of the Euclidean distances, we're using these visual distances, all right? But now the nice thing is the following. Let's look at this cross ratio. So here's my point x. I have 4 points, xi, eta, say xi prime, eta prime. What is this cross ratio? So each of these is e to the minus Gromov inner product. So Gromov inner product gives me 4 triangles, right? Like this. And then these sides of the triangles come with pluses and minuses from the Gromov inner products. So for example, rho x of xi eta, this is e to the minus Gromov inner product. So, so this cross ratio will be e to the half and then I'll have these distances. So this comes with a plus, and these two will come with minus and minus, right? Because this is minus the Gromov inner product. Similarly, this will come with a plus, and these two will come with minus and minus, right? But now these two terms on the denominator, this xi eta prime, this is e to the minus Gromov inner product on the denominator, so it goes up. It's e to the plus Gromov inner product. So this will come with a minus, and these two will come with plus and plus. This will come with a minus. These two will come with plus and plus. So what happens? What happens is that all the terms in the middle, the vertices, the sides adjacent to x, all of these come with pluses and minuses, so they cancel, right? So what happens is this actually becomes an alternating sum of infinite distances, which does not depend on x at all, right? X is no longer in this picture. Is this clear?
Yes.
So this is independent of x. Right? So that means that for all x, y in x, the cross ratio with respect to rho x is equal to the cross ratio with respect to rho y. And so therefore there is a canonical cross ratio. Independent of choice of visual metric. On boundary x. Okay. Is this clear? Yes?
Yes.
Now, what is our main example? Example, we take x to be hyperbolic space, which is, I take the ball model. So then the cross ratio, I can write as the cross ratio with respect to the visual metric based at the origin, right? But the visual metric based at the origin in the ball, we saw that this was half the caudal metric, right?
Yes.
So then this becomes nothing but just the usual Euclidean cross ratio, right? Yes? Okay. So the cross ratio defined in terms of distances in the inside, it turns out to be just this Euclidean, the usual Euclidean cross ratio on Sn minus 1, right? Is this clear?
Yes.
Okay. So this cross ratio on the boundary of a cat minus 1 space, you can think of as a generalization of the usual Euclidean cross ratio on Sn minus 1. Okay. And so we can define now, like we defined, so we know what are Mobius maps in Rn union infinity. They're maps which preserve the Euclidean cross ratio. Similarly, I can define if x, y are cat minus 1 spaces, then a map f from del x to del y is Mobius if it preserves cross ratios. All right. So we have a cross ratio on del x, we have a cross ratio on del y. F will be Mobius if it preserves cross ratios. Okay. So if X and Y are hyperbolic space, then this is a map from, so suppose, I mean, for example, if X is equal to Hn plus 1, Y is equal to also Hn plus 1, and boundary X, I take this as the upper half space model. So then boundary X is Rn union infinity, which is boundary Y. And the cross ratio is the usual Euclidean cross ratio. So Mobius map is just a usual Mobius map of Rn union infinity. Okay. So it's an element of the Mobius group of Rn union infinity. Okay, which is the group generated by reflections and inversions. All right. Yes. Is this okay?
Yes.
Okay. Now notice something. If F is an isometric embedding between cat minus 1 spaces, okay, then F is going to send geodesic rays in X to geodesic rays in Y because it's an isometry, right? And so therefore, it will induce a map from boundary to boundary, right? Because equivalent geodesics in X will go to equivalent geodesics in Y, since F preserves distances, right? Yes?
Yes.
So let me call this capital F. So what we get is that F extends to a map little f from boundary X to boundary Y. But we know more about this map from boundary X to boundary Y. What will it do to cross ratios? Well, the cross ratio is expressed in terms of these distances inside, and F is preserving distances inside. Therefore, the boundary map is going to preserve cross ratios, right? Is it clear?
Yes.
So therefore, any isometric embedding extends to a Mobius map. Okay. Is this clear? An isometric embedding between cat minus 1 spaces extends to a Mobius map between their boundaries. All right. Is this clear?
Yes.
Okay. Now we can ask the question, is the converse true? So if F from boundary X to boundary Y is a Mobius map, does F extend to an isometry, capital F, from X to Y? Okay. Fine. And we can give an example of this where the answer is yes. So suppose X and Y are both equal to, say, Hn plus 1. Here, n is greater than or equal to 1. So let me take the upper half space model, right? Okay. So what is a Mobius map of the boundary? A Mobius map of the boundary is given by either reflection in a hyperplane in the boundary or inversion in a sphere in the boundary, right? Or a product of these, right? Okay. Yes?
Yes.
Okay. So now I have f from boundary Hn plus 1, which is Rn union infinity to boundary Hn plus 1, which is Rn union infinity, a Mobius map. Okay. Now, what can I do? I have my upper half space here. Well, what I can do is any hyperplane in the boundary, I can extend it to a hyperplane which is perpendicular to the boundary of the upper half space, right? I can extend it to such a perpendicular hyperplane. Yes. And any sphere, I can extend to a sphere which is perpendicular to the boundary. Yes. Right. So then the reflection in the hyperplane will extend to a reflection in the hyperplane perpendicular to the boundary from the upper half space to itself. And this inversion in this small lower dimensional sphere will extend to an inversion in the higher dimensional sphere, which will map the upper half space to itself because it makes right angles with the boundary. So it's going to send the boundary to the boundary because I mean, it preserves angles. So the boundary has to go to the boundary. I mean, well, it's already, I mean, the boundary is already going to the boundary, we know. And so then it's going to send the upper half space to itself, right? So it turns out that, so this F, therefore, it extends to F from Hn plus 1 to Hn plus 1 such that F belongs to the subgroup of the Mobius group. So T, well, okay. So let me just write it like this. The subgroup of the Mobius group in Rn plus 1 union infinity, reflections in hyperplanes and inversions in spheres which are perpendicular to the boundary, right? Okay, so this is a subgroup of the Mobius group in n plus 1 dimensions, right? Yes. This group, it turns out to be exactly equal to the isometry group of Hn plus 1. Okay, so this is something you can calculate. The reflections, it's easy to see these preserve the hyperbolic metric because they preserve the Euclidean metric and they preserve the height, right? So these are going to be isometries. What you have to check is that inversions are also isometries, all right? Is this okay? Yes? All right. So therefore, any Mobius map of the boundary of hyperbolic space to itself extends to an isometry from hyperbolic space to itself. All right. Is this clear?
Yes.
So this is a key fact, which is a crucial, well, the crucial last step in the proof of what's called Mostow rigidity theorem. So let me state it at least. And we'll see how much of the proof we can do. We don't have much time left. So theorem, let n be greater than or equal to 3. Okay. And let say Mn be closed hyperbolic n manifolds. So here hyperbolic means that sectional curvature K is constant equal to -1. Okay. All right. So these have constant negative curvature -1. All right. And suppose that phi is an isomorphism between the fundamental groups of M and N. Okay. So suppose these have the same fundamental group. Then the Mostow rigidity theorem says that actually they are isometric. Then in fact, there exists an isometry let me call it F bar from M to N such that phi is equal to the map on fundamental groups induced by this isometry F bar star. Okay. Is the statement clear? Yes.
Yes.
So therefore, a closed means compact without boundary. A closed hyperbolic manifold of dimension at least 3 is determined up to isometry by purely topological information just by its fundamental group, right? If two of these manifolds have the same fundamental group, then they are isometric. Okay. So here one crucial point is that the dimension n is at least 3. This is false in dimension 2. In dimension 2, we have lots of hyperbolic 2 manifolds which are all homeomorphic but which are not isometric. For n equal to 2, right, what are hyperbolic manifolds? They're quotients of the hyperbolic plane. So for example, if I want to get a closed surface of genus 2, hyperbolic surface of genus 2, how do I do it? Well, you know what to do. You can write this as the quotient of a octagon, right? Basically, you cut along curves like this. Yeah. right? If you cut along these four curves, you'll get the genus 2 surface as the quotient of an octagon, right? And to get a hyperbolic structure on it, to get a metric of constant curvature, what you do is you take any hyperbolic octagon in H2. So 1, 2, 3, 4, 5, 6, 7, 8. Okay. You take any hyperbolic octagon such that these sides are alternating sides are of the same length. Okay, so this side is the same as this, and this side is the same as this. Okay, and this side is the same as this, and this side is the same as this. All right. And you choose it such that the sum of angles, the sum of interior angles is equal to 2 pi. Okay. Fine. Yes. And then you take basically hyperbolic elements of the isometry group. Those will be translations along these geodesics, which are perpendicular to the sides, which will map this side to this side, and this one will map this side to this side. This one will map this side to this side. This one will map this side to this side. All right. And then you define your group gamma to be the group generated by these these side pairing transformations. Okay. So there'll be a T1 S1, T2 S2 up to TG SG. Okay. And what you can show is if the so this will be in general a 4G-gon. All right. A polygon with 4G sides. Okay. And you'll have these 2G transformations which pair sides, these side pairing transformations. And the sum of angles, theta I goes from 1 to 4G. If this is 2 pi, then it's a theorem of Poincaré that this group is discrete and acts without fixed points. And so the quotient is a covering map, and the quotient will be this genus G surface, H2 mod gamma. Okay. Is this all right? Yes.
Yes.
Okay. So here the point is that you have a big flexibility in constructing these polygons, right? So if you choose different polygons, you'll get different non-isometric surfaces. All right. You'll get non-isometric surfaces. And so all of them are homeomorphic, but they're not isometric. Okay. So in fact, the parameter space of such surfaces, what's called the moduli space. So such hyperbolic surfaces up to isometry, this is a manifold up to some small quotient relation, but essentially it's a manifold of dimension 6G minus 6, which is called the moduli space of hyperbolic surfaces. All right. So
Yes.
you have a large deformation space in dimension 2. So what Mostow rigidity is saying is that in dimension 3 and higher, the moduli space is trivial. You have no non-trivial deformations. Okay. The moduli space is trivial.
Yes.
All right. Okay, that's what it's saying. So any questions about this? Is the statement clear? Okay. So let me try and sketch for you a proof of this. Okay. And then in the remaining time, we'll just try and sketch the proof of this. Okay.
Sir, you said that moduli space, is it a manifold or all orbifold? I mean, like necessarily a manifold?
No, it's not. It's never a manifold. It's an orbifold. Yeah. It's an orbifold. So yeah, it's an orbifold. There's a. It's the quotient of a manifold, a contractible manifold, the Teichmuller space by a discrete group, the mapping class group.
The Teichmuller space is cover, universal cover, and that's a manifold. Yeah.
The Teichmuller space is the orbifold universal cover. It's not the universal cover in the traditional sense. It's the orbifold universal cover.
Yes,
So,
yes, as the more Teichmuller theory course. Yeah.
Right. So it's the orbifold universal cover. Yeah. So the Teichmuller space is diffeomorphic to R to the 6G minus 6. Okay. So you have Teichmuller space of sigma G. This is diffeomorphic to R to the 6G minus 6. And this quotients to the moduli space of sigma G, which is, well, the quotient of Teichmuller space by a countable discrete group, the mapping class group, mod sigma G. Okay, so I won't talk about this more. This is the content of a whole course, if you like. So, so I'm not going to talk about this. So, okay, so let's try and sketch the proof of Mostar rigidity. Okay. So there are various steps. So step one is to define what's called an orbit map. So we have M, since it's a hyperbolic manifold, its universal cover is Hn, right? So it's Hn mod pi 1 M, I can write it as. And N is Hn mod pi 1 N. Okay, so I fix a base point x naught in Hn. So we've got less than a minute. Let me stop and we'll start again. All right.